Alright, so this is part number 9 on the construction of hyperreal numbers. And today I'm going to start with defining halos and galaxies. So let us start with B and C, two hyperreal numbers. And I'm going to say that B is equivalent to C, so we are here defining a new equivalence relation, if B is infinitely close to C, so that B minus C is an infinitesimal. And the halo of B, which we write like this, is the set of all elements that are hyperreal numbers which are infinitely close to B. This is indeed the equivalence class of B under this new equivalence relation. It is also sometimes written mu of B and called the monad. For the galaxy, we define a different equivalence relation. The notation here is the following. So we say B is equivalent to C if B and C are a limited distance apart, so that B minus C is a limited number. And we write the galaxy of B just like that, and it is the set of whole hyperreal numbers which are a limited distance apart from B. This is indeed the equivalence class of B under this new equivalence relation. And there are a few things we can try to think of as an exercise. For example, we can try to convince ourselves that for all x which are limited number, the shadow of x is within the halo of x. That the halo of 0 is the set of infinitesimal number, and the galaxy of 0 is the set of all limited numbers. I've added a few things here which I'm not going to take the time to talk about, but I invite you to pause the video and convince yourself of those properties or those equalities. Another exercise that I found in the book of Goldblatt was to show that the sinus of epsilon 1 being an infinitely small number, infinitesimal, is infinitely close to 0. I should say that this sinus function here is a hyperfunction, so the notation I tend to use is the following, but we drop indeed those stars when we are used to what we do. But just as a reminder, the sinus function is given by the equivalence class of the sequence which is constant and in which you have the sinus function. And epsilon 1 is an infinitely small number, so it is given by the equivalence class of a sequence of elements an, and the limit of an tend to 0. And so sinus of epsilon 1, this time as you can see I dropped the stars on both sides, is the equivalence class of the sequence of sinus an. And so what I can do now is compare sinus of epsilon 1 with epsilon 1 by looking at this equivalence class here of the sequence which is sinus an minus an. And I can use, for example, the Taylor expansion of sinus an to see that this, whatever is left here, is converging to 0 as n tend to infinity. And so that tells me that sinus epsilon 1 minus epsilon 1 is an infinitely small, an infinitesimal number. And so sinus epsilon 1 is equivalent to epsilon 1. But we also know that epsilon 1 is equivalent to 0, or what it means it's infinitely close to 0. And so by the property of transitivity of equivalence relation, I deduce that sinus of epsilon 1 is infinitely close to 0, which answers the question here. You can do the same kind of proof by considering the following: cosine of epsilon 1 equivalent to 1, or sinus epsilon 1 over epsilon 1 is equivalent to 1. The proofs that are given in the book of Goldblatt are based on the transfer principle, and I haven't talked about the transfer principle yet, so I had to proceed a different way. But a video on the transfer principle is to come soon, I promise. Another exercise here is to show that for every hyperreal number A, there exists B, which is a hyperrational number, such that A is equivalent to B, or in other words, A is infinitely close to B. So here is a notation for A, all the elements A and here being real numbers, and here is a notation for B, which would be a hyperreal number if most of the elements B and are rational numbers. And so what I suggest here is simply to build an element B that is going to be infinitely close to A by choosing every element Bn here given by the floor function of an 10 to the power n divided by 10 to the power n. And so you can convince yourself very easily that A minus B is going to be an infinitesimal, and therefore A is equivalent to B. And I give an example here by considering the hyperreal number, which is pi to the power 2n, so which is given by the following equivalence class of the sequence, which is here. And therefore Bn, I choose the floor function of pi to the power 2n times 10 to the power n, and all of that divided by 10 to the power n. So clearly every element Bn is a rational number. I give B1 here, which is 9.8, B2, 19.48, B3, which now has 3 decimal numbers, B4 that has 4 decimal behind the 37 here. And so what you see is that Bn is a number that is closer and closer to pi to the power n, and the number of decimals that tells you the precision of your number here is n. And so clearly Bn is a hyperrational number that is closer and closer to pi to the power 2n. And it is indeed infinitely close to pi to the power 2n. Okay. Another exercise is to show that R is isomorphic to this set. So this is the set of hyperrational numbers which are limited, factored by the set of hyperrational numbers which are infinitesimals. So what we really want to do here indeed is to show that R is isomorphic to the ratio of those two sets, which I'm going to write Q like this because this is tiring to write every time. So first, let's clarify what is the set Q here. So Q is the set of equivalence class X, where X are elements of the limited hyperreal numbers, and the equivalence relation here is defined by y minus x being in the set of infinitesimal hyperrational number, infinitely small hyperrational number. So the equivalence class of X is all the elements Y, such as y minus x is one of those infinitely small hyperrational. And I'm going to use the notation y equivalent to x to express the fact that y and x belong to this set. Okay, so one of the first things I need to do is to make sure that I can define an addition and a multiplication between equivalence relation. And to check that, we check the compatibility of addition and multiplication with this equivalence relation. And so I have to show that if x is equivalent to big X and y equivalent to big Y, then x plus y will be equivalent to capital X plus y, and x times y will be equivalent to capital X plus y. This is not particularly difficult to do, and once you've done it, you can indeed define addition and multiplication of equivalence class as the equivalence class of the addition and the multiplication. And so now you are in a position to define the function f, which takes elements in Q and map to R. And the idea is to define the function like this. For every equivalence class, you take the shadow of X. The first step is to show that f is a homomorphism, and this is very easy to do. You just start with f acting on the composition of two equivalence class. The composition here could be an addition or a multiplication. So this is equal by definition to f acting on the equivalence class xy, which is by definition equal to the shadow of xy, and again I can write this like that. The shadow of x, I can write it f of x, the shadow of y is f of y, And so I see now that f is by definition a homomorphism. And I am left with having to show that f is a bijective function. And so I need to show that f is surjective, and a little on later I need to show that f is injective. So to show that f is surjective, I need to show that there is an element y, for all element y, sorry, that are real number, there exists an equivalence class x in Q such that f of x equal y. Or in other words, there is an element x in the set of limited hyperrational numbers such as the shadow of x is equal to y. In other words, again, I need to show that x minus y is infinitely small, an infinitesimal. So if y is already not, yes, a real number, but even a rational number, then it's very easy to understand that y is also a limited hyperrational number, and therefore f of the equivalence class of y is y. So all we have to worry about is the y that are irrational numbers. So if I take y which is irrational, I can build this element x which is a hyperrational number. So you see, to build x, I take the floor of yn and I divide this by n, where n here is an unlimited hyperreal number. So this quantity here will be the greatest hyperinteger that is smaller than yn. And so now I can compare x to y and take the absolute value of that. And so I see that this is equal to that quantity which is here, which is always going to be smaller than 1 over n. And so this is telling me that x minus y is infinitely small, it's an infinitesimal, and therefore f of x will be equal to y. Yeah, and that is the end of the proof of the surjection property. So finally, you have to show that the function f is injective. What you can do here is work by contradiction, and so that function is injective. Okay, and so finally, if I go back to the beginning to see what we have seen, what we have done, we have been able to show that R is isomorphic to the quotient here, which is given by the set of limited hyperrational number divided by the set of infinitesimal rational number. And that is the end of this video. I'm going to prepare the next one.